This is a short video to try and explain to you the processes operating at destructive plate margins. Now, destructive plate margins occur when two lithospheric plates converge, as you can see in this diagram here. This plate is going in this direction and this plate is going in this direction. Now, this convergence is due to the Earth's internal heat, which comes from the centre of the Earth, causing convection currents to occur in the mantle. Destructive plate margins include two types of plate boundary. These two, which are subduction zone destructive plate margins, and this one, which is a collision zone destructive plate margin. In subduction destructive plate margins, the convergence can involve either two oceanic lithosphere, as we see here, or one oceanic lithosphere and one continental lithosphere. In the case of the oceanic to continental, this one here, it is the denser oceanic lithosphere, which has a density of about 3.0 to 3.3 grams per centimetre cubed, that's forced to subduct underneath the lighter, more buoyant continental crust or lithosphere, which has an average density of only 2.7 grams per centimetre cubed. In the case of the oceanic to oceanic destructive plate margin, it is the older and colder of the two oceanic lithospheres that is denser, and therefore it is this one that is forced down and subducts. In the collision zone destructive plate margins, neither of the continental lithospheres can subduct because they're too buoyant, and so one is forced over the top of the other, causing thrust faults. Okay, let's take subduction zones first. A key process at destructive plate margins at subduction zones is the generation of earthquakes. In both cases, as the solid, rigid subducting plate is being forced down underneath the other plate and into the mantle, it causes earthquakes all along its upper surface here. This zone is known as the Benioff zone. And earthquakes occur from near the surface all the way down to approximately 700 kilometres below the Earth's surface. Now you get shallow focus earthquakes here, intermediate focus earthquakes, and then the deep focus earthquakes. And they're all due to the upper edge of this descending plate getting stuck as it tries to force its way down into the mantle. Now, as it gets stuck due to friction, pressure builds up along here, and every now and again the friction is overcome, and the pressure forces the subduction plate further into the mantle, causing an earthquake. Now, another special type of earthquake occurs at subduction zone plate boundaries, and these are known as megathrust earthquakes. These occur when this plate is subducting down and it catches, due to friction, the overlying plate. Now the overlying plate starts to bend and buckle and bow and gets pulled down or dragged down with the subducting plate. Over time, masses of pressure builds up, and this can take up to over 100 years or even 200 years to build up. But eventually the friction is overcome, the pressure is released, and the overlying plate flips back or rebounds back to its original position, which sets off a huge earthquake, usually in the scale of 7, 8 or 9 magnitude. Just like the Tohoku earthquake in 2011 in Japan, where the Eurasian plate was being pulled down by the descending Pacific plate, and this has been happening for hundreds of years, and eventually the Eurasian plate couldn't take the build-up of pressure anymore and flipped up. Now, if there's an ocean over the top of these two plates, the rebounding overlying plate will displace huge amounts of water, which eventually will form a tsunami beneath there. The second key process at destructive plate margins is the generation of magma and the formation of volcanoes. As the subducting plate here, oceanic lithosphere in this case, descends into the mantle, then water from the ocean, which is mixed up in the sediment, gets dragged down the subduction zone. And about 100 kilometres down, this water is eventually released into the overlying mantle, which is made of peridotite. Now, water has the effect of lowering the melting points of the rocks in this zone. So you start to get partial melting, blobs of magma or liquid starting to form. And as you're partially melting the peridotite, you get blobs of basaltic magma starting to rise. Now this will rise up because it's less dense than surrounding rocks and build up at the base of the lithosphere. Now cracks and faults due to the tensions subjected to the lithosphere from plate collision, this magma will start to rise up through the cracks. As it does, it picks up silica from the surrounding rocks, which contaminates the magma, making it become andesitic. So we have the rock peridotite here, which turns into a basaltic magma, a liquid, and due to contamination further up becomes andesitic. Now this andesitic magma is much more viscous than the basaltic magma. This increased viscosity affects the explosivity of the magma. Any gases dissolved in the magma come out of solution as the magma rises. However, due to the viscosity of the magma, these bubbles cannot grow and expand as the magma nears the surface. I'll draw a diagram to show you. If we have our volcano here and we took a close-up of the magma, this is the magma reaching through here. If we did a close-up of that, we would see in the vent the gas bubbles staying the same size all the way up to near the top of the vent where the crater is. That's because of the viscosity of the magma stopping the gas from expanding. But eventually the pressure in the gas bubbles is too much for the magma to withhold, and it explodes violently to form an explosive eruption. Successive explosive eruptions will form a stratovolcano, which is a steep-sided cone volcano, and the hazards are pyroclastic flows, ashfall, violent blast, lahars, and landslides. An example of this type of plate boundary is the volcano of Mount St Helens, which erupted in 1980. Here, the Juan de Fusa oceanic lithosphere is being subducted underneath the North American continent. So the North American plate here, and Mount St Helens is the stratovolcano on top of the continental area. The whole process where water is released into the mantle, which lowers the melting point of the rocks, is known as hydration melting, and is the process that enables the generation of magma at a subduction zone. Lastly, let's look at the processes operating at collision zone destructive plate margins. As we said before, collision zone destructive plate margins involve two continental lithospheres. and as they are both very buoyant, they cannot be subducted, so no subduction can occur. And if no subduction can occur, no water can be dragged down, the melting point of the prototype rocks can't be lowered, and hence no magma can be generated, and there's no volcanoes. However, earthquakes do occur. Now, as one plate hits the other, one of them is actually forced over the top of the other, like this. And this here becomes known as a thrust fault. That's because one plate is literally thrust over the top of the other. And earthquakes obviously occur here because friction stops the movement occurring all the time. The pressure builds up. Eventually the pressure overcomes the friction, and there's a sudden release of pressure as the plate lurches forward, and an earthquake occurs along this boundary, and seismic waves radiate out everywhere to cause earthquakes. An example of this is the 2008 Sichuan earthquake in China, when India here is forcing its way over the top of Asia, generating large earthquakes. As a consequence of this continued movement and episodic lurching of the continent forward, we get large fold mountains forming on the surface, such as the Himalayas.